This lesson is on graphing absolute value inequalities. I'd like to point out that every time you solve absolute value inequalities, you first want to isolate the absolute value, then split it, and then graph each. Let's look at the first example. You'll notice this example only has x, so it's going to be very similar to the examples we've had in the past, except this time we're going to graph it on a Cartesian coordinate system, implying that since the y is not present, the y can be anything, but the x's are bound to certain conditions. Let's check out those conditions. If it's less than or equal to 4, a between statement. So it has to be greater than or equal to -4 and less than or equal to 4. So before we looked at it as one statement like this, between -4 and 4. That's nice and easy to solve, which then, it becomes add 1 to all three parts. You get x between -3 and 5. But this is actually two equations, this part and this part. So this is actually x greater than or equal to -3 and x less than or equal to 5. You'll notice you could have also split them at the beginning into x minus 1 greater than or equal to -4 and x minus 1 less than or equal to 4. Either way, those will result in the same solution as this. So let's try to look at both of these components. We've got x greater than or equal to -3. So if you look at the boundary of x equals -3, x equals -3 right here, that's a solid line, and x equals 5 is the other boundary, and that's right there. We want all our x's to be greater than or equal to this one, the common part, because it's an and statement. So really, you're just getting everything inside there, but not outside of that. This other one also has very similar structure. You'll notice there's no y, so it'll be very similar. Because it's greater than, we want the outskirts and not including the boundary points. So either x plus 2 is greater than 3 or x -3. So when we solve that, we get x is greater than 5 or x is less than -1. Similarly, we look for the boundary. This time, when x is greater than or equal to 5, 5 is right here. It needs to be dotted because it's including, and it's going to be everything bigger than that. X's are less than -1, so negative here, it's also dotted, and all the smaller points will be shaded. So there's an example of the answer there. All right, let's move on. Now let's look at some examples with both x and y. So again, our absolute value is on its own. That's great. Always do that first before you get to this stage. Now, since we've got a less than 3, remember, it's going to be between -3 and 3. So it's going to be x minus 1 is greater than -3, and x minus y is less than 3. You can see less than 3 and greater than -3. Okay, so let's look at both of these. The first one, if we solve for y, we'll have -y greater than -x minus 3, but we want to change the signs, so our inequality sign will also change like so. So to graph this, we have starting at 3, we move with a slope of 1 over 1, And because it's not equal to, it's a dotted line. And it's going to be everything less than. Less than implying the bottom portion, but you can always check a test point like 0, 0 to see if it's true, and yes it is. Let's try this other one. Solve it for y. Similarly, you're going to now have to change the signs. So this one starts at -3 and travels up 1/1 as well. It's also dotted, but it's greater than. So 0 is going to be true, so we're shading the top portion. An and statement, we want just the common bits. So you can imagine all the points between these two lines are going to represent the solution. More example here. This one's greater than or equal to 2. So we're going to have x minus y is greater than or equal to 2, or x minus y is less than or equal to -2. So it's on the outskirts, and it includes both components, not the intersection. So if we solve each of these similarly as before, we're going to get the following. The second one starts at +2 and travels also at the same slope and is including the line, but this time it's greater than. And because it's an or statement, we include both.